last topic in this unit is how to take a limit. Now limits are a bit of an obscure little technique that hasn't been necessary up until this point. And so it will be very difficult to explain to you what it is or why it is at this point. This is one of the skills in math where it's maybe easier for you to learn how to do it first, and then after you've mastered that, then we'll be able to do some problems that are complicated enough that this technique is required. So if you're wondering why I'm doing this, that's a good question, because at this point it shouldn't make any sense why I need to use this particular technique. Just squint your eyes and trust that this is going somewhere very shortly. Okay, so a limit is where instead of dropping a number into an equation, so instead of writing evaluate f at 4, so instead of telling you to put in 4 for your x value, I'm asking you to creep up on the value of 4. Why would I need to do that? Well, I told you not to ask that question. So we're going to do this first one, and it's pretty straightforward. So I've got it written this way, and I'm just going to parse that in English for you. That says, take the limit of 5 minus x as x approaches 4. So that's the sentence that's coded in this particular notation. Notice I've used an LIM. That will get lazier and lazier as we do these examples. When you see this symbol or something like that, it's a limit asking you to take the limit of this particular function as it approaches this particular value. So how do you do that? Well, taking a limit basically means pick a number that is very close to, but not exactly, this. So if I were to pick a number that was very, very close to 4, I might try 3.99. So I'll do that. Try x equals 3.99. So if I were to do that in this particular example, I would take 5 and I would subtract this number that is very, very close to, but not quite 4. And if I did that, I would end up with 1.01. Good so far? Now the trick to taking a limit is once you've picked some number that is close to the value in question, you have to pick another number that's even closer. So can I get to closer to 4 than this? Well, I could if I added some more 9s to the end. 3.9999. Well, if I did that, I would have to take 5 and subtract this number, 3.9999, and I would end up with 1.0001. Okay? Now, just to be nice and clear and to know that you've done it enough times, I like to try 3 numbers. Usually after 3 numbers, I can see a pattern forming in the answers, and that's ultimately what we're going to need to do more complicated versions of this type of question. So for a third number that's even closer to 4 than that, I'm just going to add 2 more 9s. 99999. It's 5 minus 3.12345. 9s equals 1.12451. Okay, lovely. So here's the trick and the art of taking a limit. I want to look at this column here. I want to see what's happening to these numbers. So as I go down the list, my x is approaching 4. So as x, I can put those together, as x approaches 4, having a hard time writing today, approaches 4, what's happening to this? Well, this number is almost 1. This number is even closer to 1 than that was. And this number is even closer to 1 than that was. And if you look at the pattern, the more 9s I put on this, the more 0s I end up here. So as these numbers are creeping up to 4, this is settling down onto 1. So as x approaches 4 from below, five minus x approaches 1. From above. So there, you've done it. You've taken the limit of 5 minus x as x approaches 4. So there's two parts to it. The first one is trying 3 numbers that do approach this value and calculating what the output is approaching. And then actually acknowledging that as x is approaching 4 from below, 5 minus x is approaching 1 from above. Now, we could have saved ourselves an enormous amount of time by just taking the number 4 and putting it here. And 5 minus 4 is, well, it's 1. That's okay. You could put that number in there, see what happens. And it's all right as long as you have a function that's going to behave itself. So we have a slightly more complicated one here, but it is the same type of question. So I see this limit here, and so that's asking me to take the limit of, so determine the limit of x squared plus 3x plus 2 divided by x minus 4 as x approaches 3. So in order to do that, I'm going to start with my guesses for x. So I'm going to start with x is 2.9. I think that's a pretty good start. So I'm going to have to take my 2.9 and in it goes 2.9 squared plus 3 times 2.9 plus 2 divided by 2.9 minus 4. And so I'm going to work that out in 2 steps. I'm going to do the numerator and the denominator so we can see them. So 2.9 squared plus 3 times 2.9 plus 2 is 19.11, and 2.9 minus 4 is minus 1.1, and then I have to divide the top by the bottom, so 19.11 divided by negative 1.1 gives me 17.37. 27, presumably forever. Now, just a sort of housekeeping note, I would strongly suggest that you do this. When you have a complicated expression with a great big division sign through the center, work out the numerator, work out the denominator, and then do the division. If you try to enter this all in one go, the frequent calculator error is this squared plus 3 times this plus 2, and then you type divided by 2.9 minus 4. And what it does, the way your calculator reads that, is it does the top correctly, divides it by 2.9, gets the answer, and then subtracts 4 from that. And that's not what you wanted. You wanted to divide by negative 1.1 here, not divide by 2.9 and then subtract 4 from the total. So think about that. Calculator skills are critical at this point to make sure you do your data entry properly. What were we doing? Right, the limit of that thing as x approaches 3. So I've done one, I need to do another one. X is 2.99. That's getting closer to 3. So I'm going to have to take 2.99 and square it, plus 3 times 2.99 plus 2, and divide by 2.99 minus 4. So I'll do the top there. 2.99 squared plus 3 times 2.99 plus 2 equals 19.9101. And the bottom, 2.99 divided by 2.99 minus 4 is negative 1.01. And if I do 19.9101 divided by negative 1.01, I end up with 19.71 29703. Okay, so one more. X is 2.999. That's getting closer. I'm not going to fill this part out because I think you see the idea. So I'm going to have to take 2.999 squared. Just shove it in there. So let's see. 2.999 squared plus 3 times 2.999 plus 2 equals 19.991001, and the bottom 2.999 minus 4 would be 1.001, and 19.991001 divided by negative 1.001 gives me negative 19.97102997. Alright, so I picked 3 numbers that got ever closer to 3. I calculated what the output was doing as I got ever closer to 3, and we're going to take a look at the numbers in this pattern and see if we can figure out what it is. So it looks like as x approaches 3, I guess I wrote this in words before, didn't I? As x approaches 3, from below, comma, x squared plus 3x plus 2 over x minus 4 approaches well, we're going to have to think about that. I had a number, it was 17, and then 17 became 19.7, and then 19.7 became, oh, those should also be negative. Blurg. Became negative 19.97. So what does it look like this is getting closer to? To me, it looks like it's getting closer and closer to 20. So I'm just going to pop that down there. Approaches negative 20. Because that's what the pattern looks like to me. And when we're doing limits, that's good enough. If I wasn't sure, if I think this might pop over 20 instead of slowly approaching it, I could always do another row. I could do 2.999999. And if that's not enough, I could do 8 nines. And if that's not enough, I could just fill my whole calculator screen with 9s until I got a pattern here that I was confident in. In the last example, we did pull a dirty trick of just dropping the 3 into the pattern. So I'm going to do that, and we'll see what I get. So if I just use the 3 squared plus 3 times 3 plus 2 over 3 minus 4. Well, 3 squared is 9. 3 times 3 is 9. That's 2. 3 minus 4 is minus 1. 9 plus 9 is 18, plus 2 is 20, divided by negative 1 is negative 20. So, of course it's approaching negative 20, because that's what it's equal to when x is 3. Obviously. And this is the part where you're asking yourself, why am I doing this? Because I could just drop the number in and calculate it. And that's fair. And whenever you're asked to do a limit, this should be the first thing you try. Take that number, drop it in, see what you get. If you get a whole number, then you're done. That's the answer. The tricky part is when you drop this number in and it doesn't work for some reason. And just to show you that, I have our next example. So I have this limit. It doesn't look any different than the last one we did. The parabola on top and a line on bottom, and I'm just trying to sneak up on this number. So in the last two examples, I was able to just drop this value into the function and get the answer. So why not try that now? So on top there, I would have 5 squared minus 8 times 5 plus 15. And in the bottom, I would have 5 minus 5. Okay. So 5 squared is 25. 8 times 5 is 40. And plus 15 is plus 15. And 5 minus 5 is, well, 0. And that's a problem, because you can't divide by 0. We'll get to that in a second. But even if I look at the top, 25 plus 15 is 40. 40 minus 40 would be 0. So I get this. Uh-oh. So what is the answer to 0 divided by 0? Because it says that like if you have a fraction like thirds, if you put a 0 on the top there, that's none. Right? 0 thirds is worth nothing. 0 fifths is worth none. 0 over 10,362 is 0. If you put a 0 in the top of a fraction, it's always worth nothing. But if you divide something by itself, like 5 out of 5, that's always equal to 1. 15 divided by 15 is 1. 156 by 156 is 1. So is this 0 because of that? Or is it 1 because of that? Or when you divide by 0, so third example, and this one is a little more abstract. If you take a number like 6 and you divide it into 0 pieces, this says take $6 and divide it amongst 0 friends. Now tell me how much each friend gets. Well, there weren't any friends, so nobody gets anything. But that $6 has to be distributed somehow. So how much does everyone get? It's a bad question, right? It's undefined. So there's a symbol for that. You might read this as infinity, but it means undefined. And that word there, infinity, means something is infinite. Right? Infinite. See that word in there? It's about definitions. This is undefined. So this fraction has one of three answers. It's either worth nothing, or it's worth something, or it's worth everything. It's true, that covers all the bases. We have to figure out which one it is. Fortunately, we're talking about limits, so this only happened because I put in exactly 5. So instead of putting in exactly 5, I'm going to pick something that's close, but not quite. So I'm going to try x is 4.99. So in order to work out the value of that, I would have to take 4.99 and square it, minus 8 times 4.99 plus 15, and divide it by 4.99 minus 5. And so that's going to give me 4.99 squared minus 8 times 4.99 plus 15. 15 is negative 0.0199. On the bottom here, 4.99 minus 5 is negative 0.01. And if I do the top divided by the bottom, I end up with 1.99. Okay. Now when we do limits, you should pick 3 numbers that are getting ever closer to the value you're approaching. So I'm going to get closer with x is 4.9999. So I'm going to have to put this here, here, and here and work it out. So I'm going to do that for the numerator. 4.9999 squared minus 8 times 4.9999 plus 15 is negative 0.00019999. And the bottom will be negative 0.0001 for a total of 1.9999. All right, one more, just because 3 is the magic number. X is 4.999999. I bet the answer is going to be 1.999999, but let's just do it to find out. 4 and 6 nines squared minus 8 times a 4 and 1, 2, 3, 4, 5, 6 nines plus 15 gives me negative 0.000001, 2, 3, 4, 5, 1, 2, 3, 4, 5, 2. And the bottom, 4.999999 minus 5 would be negative 0.1, 2, 3, 4, 5 zeros and a 1. And if I do this divided by this, negative 0.1, 2, 3, 4, 5 and a 1, I get 2. So I'm going to ask myself, as x is approaching 5 from below, what are these doing? What's the pattern happening here? From here to here to here. It looks to me that, I'm just going to get rid of this line here, that as x approaches 5 from below, x squared minus 8x plus 15 divided by x minus 5 approaches, well, what are these numbers getting closer to? And this gets closer to this and this gets closer to 2. It looks to me like this answer is converging on a value of 2 from below. So this is an example of one where you couldn't just dump the number in. You actually had to do this. You had to do a few of them to make sure that you were actually approaching a specific number, not just having these ballooning bigger and bigger as we went along. So the answer to this then, the limit as x goes to 5 of this, is this sentence here. And I need you to provide me that whole sentence. There is more to this, and if you're watching this on YouTube, you can scream at me in the comments for being imprecise. But this is just the meat of it. I want you to be able to show me that you can get that much done. So I'm going to show you a little trick, though, with this particular example. If you were really good at factoring in grade 10, you may have already noticed this thing up here factors cleanly. X squared minus 8x plus 15. If I split that into two binomials, I need x times x to get x squared. And I need two numbers that multiply to 15 and add to negative 8. Well, that would be 3 and 5, because 3 times 5 is 15 and 3 plus 5 is 8. And in order to make it negative, I just have to make those negative there. So when I factor this, do you notice that I have a factor of x minus 5 on the in the numerator and a factor of x minus 5 in the denominator? Those two things divide out if x is not 5, because you're not allowed to divide by 0. And I think you did this in grade 11. You were dividing out factors, and you had to write in that statement at the end. So this is why, so that you'd be ready to handle this particular topic. If x isn't 5, then I'm allowed to divide those out. And since I'm taking a limit, I'm not actually making x 5. I'm making x get closer and closer and closer to it. So this is a bit of lawyering. I'm allowed to divide those out if x is not 5. And then I have to follow those rules, and I have to creep up on 5 but not actually use it, because I already said I wouldn't. So if I do that, these divide each other out. My new question then is calculating the limit as x goes to 5 of x minus 3. So if I pick numbers that get closer and closer to 5 in this, without actually doing it, that's another lawyer trick. Say that you're going to follow the rules and then be not quite honest about it. Take your 5, pop it in there. 5 minus 3 is, well, it's 2, which we already knew by doing the sneak up method. So when you're doing limits, the first thing you should try is taking this number and putting it into the equation. And it might just give you the answer, and then you're done. The second thing you should consider trying is factoring. If you can factor, you may be able to divide out terms, and then you'll be able to just plunk the number in, and you'll be done, which is fine. If all else fails, if it can't be factored, you're going to have to do the 3 numbers, try this, try this, try this, creeping up and getting closer and closer and closer. So that said, there's a little thing we need to talk about here before we continue. When I tried dropping this number into this expression, I ended up with 0 divided by 0. And I had this whole conversation about that is either worth nothing, or it's worth something, or it's worth everything. And the only way to figure it out is to do some trickery with factoring, or manually enter in 3 numbers that approach. So this little structure here, because that's the trigger for all of these more complicated processes to solve this question, this thing gets a name, and this thing is called an indeterminate form. So what that's saying, that word, it means that this thing, the way it's written, isn't enough to come up with a value, because the question doesn't make any sense. So if I were to parse this in terms of cookies and friends, because that seems to work, if there are no cookies on the table and nobody shows up to take any, when do you run out? Well, you ran out before you started, so that's an answer. Or you never run out because nobody actually shows up to call you on it. Or after standing at the table for 8.5 hours, you get bored of looking at a table with no cookies and a room with no friends, and you just walk away from the experiment. So in that context, right, this doesn't have an answer. So there are two other ways that you can get something that doesn't have an answer because it's an indeterminate form. The other one would be take an infinite number of cookies. So that's an uncountable, never-ending amount of cookies, and divide them amongst an infinite number of friends. How many cookies does each person get? Well, if you took an unimaginable and possibly infinite number of cookies and divided it by an infinite number of friends, they might each get 1 or 2 or none or infinity. And this doesn't have an answer. It is also an indeterminate form. The third one that you have to watch out for is 0 multiplied by infinity. And this one's indeterminate, because if you do 0 times anything, the answer is supposed to be 0. If you do infinity times anything, it should be infinity. But if you multiply these two things together, which one wins? Is it 0 because you multiplied by 0, or is it infinity because you multiplied by infinity? And what's really fun / annoying is that sometimes it's neither. It's a number in between, like 6. And the only way to figure it out is to actually execute this limit process. So when you're hunting for limits, if you're asked a question like that, first thing you do, you dump this number in there. If you get a number, great, you're done. If not, if it generates one of these indeterminate forms, then you try factoring, or you try the manual input method in order to creep up on the value to see what you get. Alright, so in this example, find the limit as x approaches 2 of this expression. So method 1 is always take the number, drop it in, see if it works. So I'm going to do 2 squared, which is 4, plus 2 times 2, which is 4, minus 8, over 2 squared is 4, 4 times 2 is 8, plus 4. So 4 plus 4 is 8, minus 8 would be nothing, and 4 minus 8 is negative 4, plus 4, which should be nothing. And this is one of our indeterminate forms. Which means I'm going to have to use the factoring method or the approach method. So I'm going to look at that one up there, and I'm going to see if I can factor it. So I'm still trying to take the limit as x goes to 2. If I split the top, I need two numbers that multiply to 8 and add to 2. Well, plus 4 and negative 2 will work. 4 times negative 2 is negative 8. 4 minus 2 is plus 2. If I try and do the denominator, I need two numbers that multiply to 4 and add to 4. Well, that would be 2 and 2. Both negative, because minus 2 is minus 4. And then if I look at what I have there, these two things divide out as long as x doesn't actually equal 2, because 2 minus 2 would be 0, and I'm not allowed to divide by 0. So I'm left with the limit as x goes to 2 of x plus 4 over x minus 2. Alright. So I'm not allowed to drop this number right in, so I'm going to have to test. So I'm going to creep up on 2 from below. If I try x is 1.99, my top would be 5.99, and my bottom would be 0.01, giving me 5.99 divided by 0.01 is 599. If I try and get a little closer, I'd end up with 5.9999 divided by 0.0001. 5.9999 divided by 0.0001 is 59,999. Now, I'm not going to do the third row, mostly because I've ran out of space. But look what's happening. I already had a big number, and then it became much, much larger. This next one is going to be much, much larger than that. So what's happening to these numbers? As I creep up on 2, these get bigger and bigger and bigger. To what end? Well, what's the biggest number you can have? Well, that would be infinity. So we did some factoring here. Well, first we plunked the number in and found our indeterminate form, so that wasn't going to work. And we tried some factoring and tried to plunk the number in, and that wasn't going to work. So then I had to do this approach method, and I ended up with these numbers spiking off to forever. So for this question, what's the limit of, as x goes to 2 of this expression? As x approaches 2 from below, x squared plus 2x minus 8 over x squared minus 4x plus 4 approaches positive infinity. Now, you notice I'm allowed to say that. I can never write equals infinity, because nothing can equal infinity, but it can approach it. The same way that I couldn't make x equal to, but I could let it approach to. So after this example, I'm hoping that you're starting to see why we use limits. That sometimes a function can't accept a number, but we're trying to figure out what it's doing around that number, so I need to creep up on it to try and get an idea. This, spiking to infinity, looks a lot like a vertical asymptote. So we're going to be using this technique later when we analyze rational functions to hunt for vertical asymptotes. All right, for the last example here, we're going to try one where nothing works. And I'm going to introduce this limit as x goes to infinity. So what this is saying in English is as x becomes impossibly large, in the positive direction, because it's positive infinity, not negative, so in the positive direction, dot, dot, dot. I want to know what this is doing. So method number 1 would be to park an park this value in for x's. So if I tried that, I'd do ln of infinity divided by infinity. Okay, so I don't know if you remember ln, but ln does this. And this goes forever. So if you go forever this way, then this goes forever that way. So ln infinity, and yes, the internet can yell at me for writing this. Ln infinity is infinity, right? It's as big as you'd like. And I've got a division by infinity there. That thing there is one of our indeterminate forms. Smiley face, because everyone loves an indeterminate form. So if it's an indeterminate form, then you have to turn to factoring or the approach method. So I'm going to get rid of this because it didn't work. And I'm going to try the factoring method. Do you know how to factor the natural logarithm? Well, that's enough of that then. If this doesn't factor, then obviously you can't use the factoring method, so we're going to have to use the approach method. So the question remains, how do you approach infinity? Well, I don't actually have to get there, remember, right? Like 1.9, 1.99, 1.9999, we're approaching 2. But I never put 2 in there, so I don't actually have to get to infinity. I just have to get close to it and then check what's happening with the pattern. So I'm going to pick a number that's, huge. Ready? Biggest number I can think of at the moment. 10. Now that may not seem very large to you, but I'd like you to think about any of the graphs you ever did in grade 10 or grade 11 and ask yourself if the x-axis ever went beyond 10. Because I bet it didn't. So that's a fairly large number as far as sketching and functional analysis goes. I'm going to try that in this function. I'm going to do ln of 10 divided by 10. Now ln, ln, that's the natural logarithm. It's log base e. I'm just going to pop that up here so that you remember that. Ln of 10 is log base e of 10. This is just a button on your calculator. So I will challenge you to find it and see if you get the same answer that I do. Ln of 10 is 2.3025. 85093. And I'm supposed to divide that by 10 then, so I would end up with 0.230. Nope, yep. 302585093. Okay, good. Now, from here, I need a number that is closer to infinity than this one is. So let's go with 10,000. That is definitely approaching infinity, and it's closer than this was. So ln of 10,000 divided by 10,000. So ln of 10,000 is 9.210340372. And I'm dividing by 10,000, which gives me, I'm going to write it here so it's not in my face, 0.000921034. Okay, now I need to get closer to infinity than this one is. I accomplished that by adding 3 zeros, so let's just do that again. 10 million. So I'm going to need the ln of 10 million divided by 10 million. So ln of 10, 1, 2, 3, 4, 5, 6 million is 16.11 8 something 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 divided by 10 million. 10, 1, 2, 3, 4, 5, 6. And I get 0.00001612. Okay, so as x becomes impossibly large in the positive direction, ... Let's look at the pattern and see what happens. When x was way out at 10, I had 0.23 as my answer. When it got further out, my answer dropped to this, 0.00092. And when I got out this far, my answer dropped to that, 0.000001612. What's happening to these numbers? It looks to me like they're vanishing. They're dropping down to 0, and they're doing it from above. So that's the answer for this question. The limit as x gets impossibly large for this particular configuration of functions, as x becomes impossibly large in the positive direction, ln x over x approaches 0 from above. So if you were sketching this function here, which we'll be doing at the end of this course, as you get closer and closer to infinity, so as I'm going out this way on my x-axis, this thing is dropping to 0. That's a horizontal asymptote. So you just determined, by using a limit as x goes to infinity, the end behaviors of your function. Now don't get too caught up in that. That's 3 units from now. But this technique is going to be helpful for finding horizontal asymptotes, so what it does way out there and way out there, and for determining whether things have vertical asymptotes, places where the functions fail.